If you follow the world of massive AI models,
Yeah.
you know the absolute monster that stands in the way of true long context understanding. It's the quadratic of technical reports. The computational costs just
Yeah.
they explode.
They really do. I mean, if you double the length of the text you're putting in, the compute needed quadruples. It's why these huge context windows of, say, 500,000 tokens are just not feasible for daily use.
So if the problem is really rooted in the math of processing sequential text tokens, what if we just change the modality entirely?
Uh-huh.
And this is where this really fascinating idea of context optical compression comes in, using an image, a visual medium, as this incredibly efficient way to carry information.
That's the core concept DeepSeek is chasing here. You take the long document, you render it as an image, and then you have a vision language model process the image. But, the big question is, how do you actually measure if that works? How do you quantify it?
And that's where optical character recognition, or OCR, becomes the perfect testbed. It's a clean compression-decompression problem.
A perfect mapping.
Exactly. The text goes in, gets compressed visually, and then the model has to decode it perfectly on the other side.
Yeah.
And that gives us these really hard quantitative metrics precision error rates.
To measure exactly how many text tokens you can reliably cram into a single vision token.
Which is the mission for our deep dive today into DeepSeek-OCR. We're going to unpack the hard math of the architecture, focusing on the numbers that led to their big breakthrough. We need to know, what is the limit?
What is that boundary for near lossless compression?
Okay, let's get into the architecture. If the goal is this kind of extreme compression, I'm guessing standard off-the-shelf vision models just weren't going to cut it.
No, they absolutely had to build a custom solution. The final system, DeepSeek-OCR, is a VLM that's split into two very optimized parts. You have the DeepEncoder, which is the compressor,
Right.
and then the DeepSeek3B-MoE, which acts as the high-fidelity decoder.
So why the custom DeepEncoder? I mean, couldn't they just use one of the high-res tiling approaches that are pretty common now?
The problem is that the standard encoders fail to meet three requirements at the same time. You need 1, very high resolution for the text detail, 2, very low activation memory to keep things manageable, and 3, a low fixed number of output vision tokens.
And the standard models force you to pick one or two of those, but not all three.
Exactly. You either get high resolution with insane memory usage, or you break the image into so many tiny pieces you end up with thousands of vision tokens anyway, which completely defeats the purpose.
Okay, so the genius of the DeepEncoder is managing those trade-offs. Let's dig into the math inside that compression pipeline. How does it even start turning a high-res image into just a handful of dense tokens?
It starts with segmentation. So they take a high-res input, let's say 1024 by 1024 pixels, and based on their patch size, it immediately gets segmented into 4,096 initial patch tokens.
4,000 tokens. Wow, that's still a massive sequence. Even for vision, that's where things start to get computationally expensive. How do they handle that?
This is the first really smart engineering decision. These 4,096 tokens, they first pass through an 80 million parameter SAM-based component, but crucially, this uses window attention.
Okay, so it's processing things locally first.
Right. It looks at features inside smaller, non-overlapping windows. This keeps the computational cost linear at this early stage, so it can extract perceptual features like characters and layout without the memory blowing up.
So window attention is the tool for efficient local feature extraction. But the whole point is to get a global understanding. How do they do the actual compression?
That happens in a tiny module, just 2 layers, sandwiched between that SAM perception layer and the global feature extractor. It's a specialized 2-layer convolutional module.
And this is the core of the compression math.
This is it. It uses a stride of 2 and a kernel size of 3, and it's designed specifically to perform a highly aggressive 16x downsampling of the token sequence.
Hold on, 16 times? That sounds like you'd lose a massive amount of information about the text.
You would if you were just, throwing away data. But this convolutional layer is trained to be a smart filter. It learns to keep the important structural information, the lines, the words, the layout, while mathematically getting rid of all the redundant feature space.
So it's a learned compression.
Exactly. And the result is that the 4,096 initial tokens are squeezed down into a much more manageable 256 vision tokens.
And 256, that is the magic number. Why is that specific number so important for the pipeline?
Because those 256 tokens are what get fed into the next component, a CLIP large model, which needs to use global attention.
Meaning every token has to talk to every other token, the expensive part.
The very expensive part. If you tried to do that with the original 4,096 tokens, the calculation would be prohibitively slow and memory intensive. By compressing 16x before that expensive global step, they control the quadratic complexity.
That makes so much sense. You manage the local complexity, compress like crazy, and then you pay the price for global context, but on a tiny, super dense set of features.
And the decoder is just as optimized, using that mixture of experts architecture.
Ah, the MoE.
Yeah.
So instead of lighting up a massive 3 billion parameter model every time.
Precisely. The decoder is DeepSeek3B-MoE. Think of it like a team of 64 specialist contractors. For any given job or token, you only call in a small, specific subset of them.
So you're only activating the parts you actually need.
Right. In practice, it only activates 6 out of 64 experts plus 2 shared ones. So you're only running about 570 million active parameters at inference time. You get the quality of a giant model with the speed of a much smaller one.
Okay, now that we understand the engine, let's get to the core quantitative finding here. This 10x threshold. What is the actual boundary of information density?
They defined a really critical metric for this, the compression ratio. It's simple, really. It's the number of text tokens in the original document divided by the number of vision tokens the model uses to see it.
And they used the Fox benchmark to test this with their low token modes, tiny mode with 64 vision tokens and small with 100. So what did the data show?
The data showed this striking consistency. When the compression ratio stays below 10x, the precision of the reconstructed text is exceptionally high. It's near lossless.
Okay, let's nail down those numbers because this feels like the critical takeaway for anyone designing a VLM.
For sure. Take a document with 800 to 900 text tokens. They fed that into small mode 100 vision tokens. That gives you an 8.5x compression ratio. The OCR precision, 96.8%.
Wow.
And even pushing it higher to a 9.7x ratio, the precision stayed locked at 96.8%.
So that 10x ratio really is the informational sweet spot. It's proof that the VLM is learning to perfectly decode content from this incredibly dense visual signature.
It is. The visual channel is acting like a super efficient bottleneck. But just like in classic information theory, once you cross that line and start overloading the channel's capacity, performance begins to degrade.
How fast does it drop off? Is it a cliff?
Not an immediate cliff, but it gets steep. Moving up to, say, an 11.3x ratio, precision is still pretty good at 89.8%. But the stress test, that really shows the limit.
The extreme end where the channel starts to break down.
Exactly. They pushed the ratio all the way to nearly 20x. They took documents with 1,200 to 1,300 text tokens and forced them into just the 64 vision tokens of tiny mode.
That's a 19.7x ratio.
And at that extreme density, precision just plummets to 59.1%. So that gives you the empirical guideline. For reliable, high-fidelity optical compression, 10x is your target.
So we have the theoretical limit. How does this translate into real-world performance on, messy document parsing tasks?
For that, we shift to a different metric, edit distance, or ED, on benchmarks like OmniDocBench. Edit distance is basically an error score. It's the minimum number of character changes you'd need to make to fix the model's output. Lower is better.
And this is where the efficiency of the DeepEncoder's low token output should really start to outshine models that just use brute force token counts.
And the difference is monumental. DeepSeek-OCR, using its small mode of just 100 vision tokens, gets an edit distance of 0.221.
Okay.
Now compare that to a big competitor, GOT-OCR 2.0. It uses 256 tokens, more than double, and gets a worse ED of 0.287.
So superior performance with less than half the computational work. That's a huge deal.
It's a staggering demonstration of the information density they've achieved, and it gets even more extreme when you look at the ultra-high-res models.
Right, the ones that push tens of thousands of tokens.
It just highlights the difference between smart compression and raw throughput. DeepSeek-OCR's intensive mode, called Gundam mode, uses fewer than 800 vision tokens per page. With those 800 tokens, it gets an ED of 0.127.
And the competitor.
A model like Miner U 2.0, to get a slightly worse ED of 0.133, needs almost 7,000 vision tokens per page.
Wait, 7,000 versus 800? That is nearly a 9-fold reduction in the input sequence length for a better result. That's where the massive savings in speed and cost come from.
Absolutely. And all this performance data ties directly back to our 10x compression theory.
How so?
Well, look at simple low-density documents like slides. They have very few text tokens, so the compression ratio stays low. They get amazing performance with only 64 vision tokens.
Makes sense.
Textbooks and academic papers, they're denser. They need the 400 vision tokens from small mode to get similar results. The model is basically scaling its resource use to keep that ratio optimized, under 10x.
But once you hit something really dense, like a newspaper page, which can have 4,000 or 5,000 text tokens.
Then you completely overwhelm the 64 or 100 token modes. The ratio goes way past 10x. The benchmarks show that for those documents, you need the ultra-high-res Gundam modes, which can scale up to nearly 1,900 tokens.
So it confirms that the VLM only demands more visual bandwidth when the text density pushes the limits of that optical channel.
Exactly.
That quantitative boundary, combined with the dynamic resolution support, tiny, small, base, large modes, it opens up some really interesting theoretical doors, doesn't it? Beyond just OCR.
This is one of the most profound implications, I think. This ability to dynamically change the number of output vision tokens, 64, 100, 256, 400, it lets the optical compression mechanism act as an analogy for how humans manage long-term memory.
Optical forgetting. I love that concept.
It's a great way to think about it. Imagine an LLM processing a long conversation history. You could render the oldest parts of that conversation onto an image. But the trick is, you don't need perfect fidelity for something that happened ages ago.
Right. Your most recent memories are crystal clear, high res. But distant memories are fuzzier. You remember the gist, but not the exact words.
Exactly that. By progressively downsizing those older rendered images, moving them from large mode down to tiny mode, for instance, you drastically cut the token cost. The text becomes blurrier to the VLM. It naturally holds on to the main points, but lets the fine details fade.
So it's a resource allocation strategy that mirrors biological memory decay. You spend a lot of resources on recent events and very few on distant ones, all to manage that quadratic burden.
You're connecting visual degradation over distance with memory decay over time. It could be a scalable path toward models with theoretically unlimited context.
So let's bring this all together. What DeepSeek-OCR has really done is more than just a performance boost. They've validated a crucial mathematical guideline. Near lossless context compression, using vision, is viable at about a 10x text-to-vision token ratio.
And that finding is foundational. It gives engineers immediate, concrete guidance on how to optimize resource allocation. It stops you from wasting compute by allocating too many vision tokens when the text density just doesn't need it.
And the practical payoff is huge. Because the system is so efficient, it's being deployed at a massive scale. They can generate over 200,000 pages of high-quality training data a day on a single A100 GPU.
That's efficiency driving scale. The token efficiency shown here really argues that the visual channel inherently carries a higher information density than our text architectures can handle. The really profound next step for research, building on this math, is to explore digital optical text interleaved pre-training.
Training models natively on this compressed visual context.
Right. Can we actually bypass the linear constraints of text forever? That might just be the future of unlimited context.
Okay, get this. What if the best way for an AI to read, say, a 1,000-page novel isn't to read the words at all, but to just look at a picture of the pages? It sounds totally backwards, right? But it's actually a massive breakthrough that could solve one of the biggest, most expensive problems in AI today. So, let's unpack this.
All right, let's jump right in. This question right here, it really gets to the core of what we call the long context problem. You know how it is, right? Even for us, if you're reading a super long book, by page 500, you might forget a detail from page 10. For an AI, it's that problem, but on steroids. It's a massive memory bottleneck. But what if the solution isn't to give the AI a better memory, but to, well, to trick it into seeing the text instead of reading it?
Okay, so before we get to this really clever visual trick, we need to understand the problem we're trying to solve. I mean, why can't a super intelligent AI just read a long book like we do? Well, the answer, unfortunately, comes down to some pretty brutal math. And this is where things get expensive. The problem is a little concept called quadratic scaling. Now, stick with me here. You'd think that if reading a 10-page document costs, say, $4, then a 20-page document would cost $8. Simple, right? Nope. With quadratic scaling, that 20-page document costs $16. You double the length, you square the cost. Now imagine feeding it a 1,000-page legal contract or a massive scientific paper. The cost just explodes. It becomes a computational nightmare. Which is why, until now, it's been basically impossible for AIs to really dig into super long texts. Now, of course, researchers have tried to get around this. But honestly, all the workarounds have been kind of messy. You've got some that are just way too complicated to train. Others try to chop the document up into a million tiny pieces, which just creates a different kind of data flood. And then there are the ones that are so memory hungry, they just crash the whole system. They're all just band-aids, not a real cure. So if the text itself is the problem, what if we just get rid of the text? This is where we get to a really counterintuitive, almost wild idea. What if, instead of feeding an AI words and sentences, we just show it a picture of the page? Could an AI actually see a document more efficiently than it can read it? It sounds crazy, but let's find out. You know that old saying, a picture is worth 1,000 words? Well, for an AI, what's the actual exchange rate? A new paper from DeepSeek-AI basically put a number on it. See, when an AI looks at an image, it doesn't see it like we do. It breaks it down into these little meaningful chunks called vision tokens. Think of them like smart pixels. And these researchers figured out the magic ratio, how to compress all those words on a page into just a handful of vision tokens. They call this method optical compression. And there it is, the core idea in a nutshell. We're literally using the power of an AI's eyes, its vision system, to solve a text problem. It's a totally brilliant workaround. And the model they built to do exactly this is called DeepSeek-OCR. All right, so how does this magic trick actually work under the hood? Let's get a little more technical and look inside the engine that makes this all possible. It's called the DeepEncoder, and its secret is a really clever 3-step design. So check out this architecture. What makes this whole thing so smart is its 3-part system. First, you've got a perception module. Think of this as the eyes. It sees the page in super high detail. Then you have the knowledge module. That's the brain, the part that actually understands the content. But the really critical piece is what sits in the middle, a super powerful compressor that acts like a filter, boiling everything down to just the essentials. It's a really simple but totally brilliant process. Step 1, the perception part, looks at the whole page in all its high-res glory. Step 2, the compressor comes in and just aggressively shrinks all that data down. And finally, step 3, the knowledge module gets this tiny compressed summary and deeply understands it. So the mantra is perceive broadly, compress aggressively, and then understand deeply. Let's really dig into the math and see what that compression looks like in hard numbers. Okay, so starting out, in the perception stage, the system looks at a single high-resolution image of a page. From that one image, it generates 4,096 initial vision tokens. Now, to be clear, that's a lot of raw data. That's the flood of information we're trying to avoid. And then the magic happens. That compressor in the middle, which is actually a 2-layer convolutional module, kicks in. Now, these modules are absolute wizards at finding patterns in images. It scans those thousands of tokens and intelligently merges and summarizes them, resulting in a massive 16-fold reduction. And what's left? Just 256 tokens. That's it. That's all that gets sent to the AI's brain. Just think about that for a second. We went from over 4,000 pieces of data down to just 256, all while keeping the essential meaning of the page intact. That is some seriously incredible efficiency. But here's the multi-million-dollar question, right? It's great to compress all that data, but it's totally useless if the AI can't understand the result. I mean, what's the point if it's all just gibberish? So does it actually work? Let's look at the data and see what the trade-off is between compression and accuracy. And this chart from the paper pretty much says it all. The results are kind of staggering. You can compress the data by a factor of 10 and still maintain an incredible 97% precision. That's insane. It's only when you really push it to an extreme 20x compression that accuracy starts to take a noticeable hit. What this means is there's a huge sweet spot where you get massive efficiency gains with almost no loss in performance. So what does this look like when you put it up against the big guys? Well, DeepSeek-OCR achieves the same top-tier performance as a massive model like Minoru 2.0, but look at the token difference. It's using nearly 9 times less data to get the same job done. That's not just a small improvement, that's a complete game changer. It's the difference between needing a whole supercomputer and being able to run on a much smaller, way cheaper setup. It is the definition of working smarter, not harder. Okay, so let's zoom out. Why does any of this really matter? Because look, this is about so much more than just reading PDFs faster. This could be a fundamental shift in how we get AI to process and remember massive amounts of information. Period. And this is a perfect real-world example of its power. The model can look at something really complex, like this bar chart from a financial report, and it doesn't just read the words sales or Q1. It understands the structure. It sees the relationships between the bars and the labels and can pull out a perfectly structured data table, like the one you see here. This is something called deep parsing, and for anyone who's ever had to manually pull data out of a chart or report, you know this is a huge deal. So, what are the big takeaways here? First, optical compression is an incredibly elegant and efficient solution to that nasty long context problem. Second, it delivers top-tier performance with just a fraction of the data. And third, it's so scalable you could generate training data for other AIs at a mind-boggling scale. We're talking 33 million pages a day. And maybe the most fascinating piece of all this, it opens up totally new research paths into how AIs might develop long-term memory or even how they might learn to forget. Look, what we're seeing here isn't just a small incremental step forward. It's a massive leap in efficiency. And it really leaves us with one final, pretty profound question to think about. If we can teach an AI to read and process information this efficiently, what's the actual limit to what it can eventually understand?